Good start.
They were two, well, two was just 3 lines, that that's called function thing.
Okay, so let's start, I guess. So I asked people to send me specific questions if they have any, but I haven't received stuff. So I'm assuming that most of you are comfortable with solutions to homework questions. So that's just something to keep in mind. So if you have questions, again, Thursday I don't plan to do anything new. So Thursday, if there's not many questions, we can even skip class so that you guys can do your projects or whatever, or we can meet very quickly. Okay, so yeah, if you have specific things that you'd like me to just talk about, just let me know. And all solutions to homeworks up to homework 4 have been posted. Hopefully all of you have seen it. And homework 5, there's still people slowly trickling in submissions. So I think we have until this Saturday officially to allow that. Okay. So, but if you guys all are okay with, if you think that I should just give some part of solution or whatever, I could do that also. Okay. So, yeah, or you can just ask the TAs; they'll be happy to help you out. Okay. So that's probably better. Given people might want to stick. All right. So. Okay, so actually any logistic questions, I should mention, of course, as all of you know, the exam is next Monday. Okay, and I think it starts at 10:30, so don't show up at this time, show up early. Okay, so same room, of course. And also, it's you can bring anything except, but no electronics. Okay, bring anything. No electronics. Okay, so unfortunately, this means that you have to print maybe a lot of stuff and bring. But I've had to do this because, as I said, last year some people started searching for things and so on. Okay, so we have to do this. Okay, so any questions about the final? Yeah.
Your Kindle is okay, right?
Sorry?
Kindle. You can bring Kindle?
I've encountered this question before, but what can you do in a Kindle? I don't know actually.
Because it has textbooks inside.
So you have textbooks, and but can you access the? I thought you could access the internet, email, and stuff, right?
No.
I guess it depends on the Kindle. Okay. So if you have something where you are just allowed to read but not access the internet, and that does not include things where you can enable internet, then you can use that. Okay, so that's this. Okay, so any other questions about the exam? So, and of course, as you know, this will be like 20% of your grade. And there's also, I will tell you, it's not as simple as this. There's also like a little bit of more constraint. I will tell you, I'll send you guys a more formal thing as an announcement. Okay, usually if you get less than 50% in the final, I don't give A's. Okay, so that's the only other rule I have. Okay, so because there are people who sometimes collaborate a lot on the assignments and somehow do really poorly on the final, and if it demonstrates that you haven't understood things, then I don't like you on it. So that's the only other thing. Okay, so but apart from that, it just contributes to 20% of the mark. Okay. Right, so any other questions? Yeah.
And since we didn't have midterms, so the finals will be pretty spread across the whole semester.
Yes. Yeah. So did you guys look at the previous finals, last year's finals? So it'll be along similar lines. So you'll get a answer sheet and you've got to write within the space provided. And in exceptional cases, you can add an extra sheet and stuff. Yeah, but that's usually about it. Right. So that's that. So I wanted to quickly recap something we did last time because not many of you were here, but we were talking about error correction, and in some sense the goal was how you do reliable computation using unreliable components. Okay? So think of circuits that produce noisy outputs and things like this. Okay? And the question was, can you do reliable computation using such components? And the way we motivated this was via some very simple games. And yeah, so the game here was simple. So suppose I think of a number between 1 and a million. Okay, and I ask you to guess the number using a small number of questions. The obvious way is to do binary search. You can say, oh, does the number lie? Is it less than this, and so on. But what if I'm allowed to lie once? Okay, so I don't tell you when I'm lying, but I'm allowed to lie once. So this was kind of the puzzle we studied last time. We said that, okay, if you have at most q lies, then how many questions do you need to ask? Right? So we saw that obvious solutions were basically repeating questions and so on, things like this. But these give, depending on q, they could be quite bad. Okay, so you've got to repeat every question a fair number of times if you want this to work. But then we saw some smarter ways of doing this. And more interestingly, what we saw last time is that in some sense there's a connection to error correcting codes. Okay, so this was what we saw last time. And one of the key observations was any query you can formalize it as membership in some set S. And now a bunch of queries can be viewed as, oh, I give you a bunch of sets, and I mean, you give me a bunch of sets, and I'm supposed to tell you whether the number I thought of belongs to those sets or not. Okay. And we said that if I'm allowed to lie only a few times, then it's like saying that some of these answers are wrong. Okay, so I can pick which answers are wrong. And then we said that, okay, you can view these membership in the sets as some kind of a code for every number. Like if I thought of the number 100 and you asked for the sets 1, 2, 4, 5, 199, and this was S1 and S2 was something like 1, 2, 4, then you can think of the number 100. The answers I'm supposed to give you are 1 and 0. So this is some kind of an encoding of the number 100. Okay, so, and we said that you basically, for you to be able to figure out the right answer, the encodings of all the numbers in the domain have to be different. Because otherwise you can't tell apart one number from the other by just the answers to these queries. And if these encodings are actually far apart, then you know that even if I lie a little bit, you can still figure out what the right answer is. Okay, so this was kind of the gist of what we did last time. Okay, so let's not get into that anymore. But so this sort of simple puzzle, so it has applications in fault-tolerant computation. Okay, and this is something that people are increasingly looking at because, I mean, so nowadays you have things being communicated between machines and so on. Now communication lines could be noisy and servers could fail and stuff like that. Okay, so fault-tolerant computation it's in a process of revival. Okay, so these kind of ideas are becoming much more nicer and cooler these days. Okay, so this is something we briefly touched upon last time. Okay, so all right. So what is today's plan? Right. So today's plan is and also the course overview. So course in 30 minutes, something like that. Okay. So we're going to do a few things. So one is I want to talk a little bit about the general lay of the land in the space of algorithms. Okay. So this is not just from a research point of view, but also from an application point of view. I want to touch briefly upon a few things that we didn't have time to do in the course. Okay, so that's what I wrote down here. Okay. And then I want to do a rough review of the full course, just to go over the kind of stuff we've done and what kind of things, what you should kind of take away from the course. Okay. And yeah, when we talk about these, we'll also talk about how it relates to stuff we've done. Okay. All right. So one thing I wanted to kind of say is that most of the course we've had this kind of a picture about algorithms, right? So broadly speaking, we had a problem that was well defined. Okay. So almost every class we started off with a problem formulation and trying to come up with an algorithm for it. Right? So we assumed that formulation is somehow given to us. Okay, so we knew exactly what we were, how we wanted to formulate this question. Okay, so this is how we did things. Then we also assumed that input is given to us. It's known fully, it's given to us. There was this one small lecture on online algorithms where we assumed this was not the case. But modulo that, we assumed that we knew the whole input. Right? And we wanted to get as close to the optimum solution, to the best solution. As quickly as possible. Okay, so this was the general goal. Okay, and also we assume that computation happens flawlessly. Okay, so anything we want to compute, you can compute up to pretty good accuracy and so forth. We never really cared about accuracy issues. Okay, so infinite precision. Okay. And yeah, so we also assumed, well, most of what we did in randomized algorithms, we assumed that you have some perfect source of randomness. Okay, so we never actually went and asked this question, where do you get random bits from? And so we always said, oh, toss some coins, do some probabilistic sampling and stuff like this. But in practice, this is actually a pretty, this is a big philosophical question which is kind of open-ended, that we don't know how to get perfectly random bits. So, like, I don't know if you guys know this, but like in the 1950s, 60s, people had books of random numbers. So, so the book would just contain a binary sequence of things, and that was like defined as random. Okay, so these were obtained by some weird physical measurements and things like this. And what we have nowadays is not much better, right? So we have seeds that you kind of hardcode, you type without looking, and that is your seed, right? So, or you take the time or something like this. Okay, so it is, yeah. So this is an aspect we never touched upon. Okay. And another very broad aspect that we never touched upon in this course is that is this last bullet. We always assumed that all our algorithms were running on a single machine. Okay. So we assumed that you have input that's all in memory, okay, and so everything was on a single machine, right? So single CPU, all input is in memory. Okay, so these are all idealistic assumptions, and in most real-life applications, one or more of these things will fail. Okay. And but it's always good to know what to do in an ideal solution, right? So that's what we do as scientists. We kind of abstract out the ideal aspects of a problem, try to solve it, and try to see how you modify it to fit it to your real-life application. Okay. So that's the general thing here. Okay, so even for analysis, we had a very similar thing, and this is something that at least this is a very this is an aspect of research that a lot of us work on. Okay, so far in the course, we've been analyzing running times, we've been proving correctness, and we've always been very careful not to make any assumptions on input. And this is, I think, in some sense, this separates what we do as computer scientists from what, say, statisticians do and so on. Okay. So basically, when you talk to a statistician, right, so when they come up with a problem, they have an input distribution in mind. Okay, so when they say clustering, in their mind, they assume that all inputs just come from some distribution, something like that. while we as computer scientists, we focus on arbitrary inputs, but we focus on the formulation in some sense. Okay, so this kind of is a key difference. And nowadays, of course, there's a kind of a joint view between these two things, and I think both communities are starting to realize that, neither viewpoint is perfect, and depending on the problem, we have to look at both. Okay, so that's so that's one of the things. Okay, but throughout the course, we've always wanted to get guarantees on the worst possible inputs and so on. Okay. So correctness, approximation, all of these things were for worst possible inputs. And we also looked at NP hardness in the same sense, right? So we looked, depending on the formulation, we wanted to either show that it's hard, wanted to understand its complexity, but most of the time we're talking about worst case complexity. Okay. So that's so this was our view on analysis. Okay. So this is something to kind of keep in mind, okay, that these are the assumptions we are making. Okay, now, so in the real world, right, so most of the time, so we, as I was saying, so one or more of these assumptions need not hold. Okay, so we've got to keep that in mind. Okay, and one thing that maybe many of you will not appreciate now is the fact that very often the problem needs to be formulated appropriately. Okay, and these are all aspects that kind of go hand in hand. Okay, so you'll have some vague goal. Okay, so you might want to you have a big graph, you might want to find sets of nodes that are well connected, right? Now how you phrase this problem is a matter of interpretation, right? So one person could phrase it one way, another person could phrase it another way. Okay. What's worse, one way of phrasing could be NP hard, the other way of phrasing could actually give you very good approximation, it could even be efficiently solvable. Okay. And that's kind of, so these two aspects kind of play one another. Okay, so you might have to phrase a problem appropriately, and but no matter how you phrase it, problems are usually NP hard. Okay, so you've got to figure out what suffices for your purpose. Okay. So sometimes a good approximation solution might be good enough. Okay. Sometimes you want an exact solution, but you want to make some assumptions on the input. Okay. So these are the kind of things you've got to look for. Okay, so you might want to seek an approximation. You might just want a weaker guarantee that, oh, if inputs are like this, then my solution is bound to be optimal, something like this. Okay, so these are usually structural assumptions. And all of these choices kind of guide what kind of algorithms you develop. Okay, so this is something that I just want to mention. And you want to also make, so this was what I was saying, you want to make some assumptions on the inputs. Okay. And again, so the reason we studied NP hardness in a fair amount of detail in this course is that this often happens in practice. I mean, you have a problem to solve, you want to formulate it in the right way so that it's somewhat tractable. Okay. And so in some sense, you've got to, very often when you're thinking about a problem, you've got to have the hardness also in mind. Okay, so you've got to say, okay, if I aim to solve this special problem, then maybe it's too hard. Like a very simple example of this is, again, going back to this graph example of you want to find a set of nodes that are well connected. So there's a very surprising fact that if you phrase the problem as you want to maximize number of edges subject to some number of nodes being a certain value, turns out to be extremely hard. If you relax the constraint a little bit, if you will say that it's number of edges divided by number of nodes, something like this, then it's actually efficiently solvable. Okay. So a very slight formulation difference makes the problem, changes the complexity a lot. Okay, and in practice, it might not matter which formulation you use. Okay, so that's what I mean by, in some sense, you've got to balance between. You've got to be able to realize, oh, if I phrase it this way, it's going to be too difficult for me to solve. Okay, so that's the reason we do NP hardness in this course in a fair amount of detail. And this other part, which we did to some extent, is you've got to know general methods of coming up with heuristics. Okay, and the kind of things we did are, so writing down local search or greedy solutions and things like this. Okay, so these are all methods to get at that. Okay, so these are all, you're given a new problem, how you approach it, kind of things. Okay, and one of the things which I hope most of you have learned from this course is, at least when you come up with a heuristic, how you analyze it, in the sense of understanding when it works, or figuring out if it's correct or not, right? So that's hopefully something you've all learned from this class, like basically analyzing correctness, and also understanding, and this also ties with this point. I mean, you might be able to say, oh, this algorithm does not work, but if I assume something about the input, then maybe it works. Okay, so hopefully you've gained some insights of this kind, right? And especially about things like local search, greedy, and so on. Okay. So I've not stated this explicitly earlier, but these are the kind of things we've been doing. Okay, so in homework and such. So, all right. So this is what algorithms in the real world would usually look like. Another thing, as I was saying, is almost, in most applications today, you've got to use parallelism, right? So you have a lot of data and can't possibly do interesting computations on the whole thing. Okay, so you either have to sample and work with a smaller amount of data, or you've got to be able to figure out some way of processing these things in parallel. Okay? So these are kind of the two ways you do things, right? So, and generally speaking, you could ask, okay, so what kind of algorithms can be made parallel, right? So this is a very, very broad, very, very informal question, but usually, algorithms that are divide and conquer type algorithms can be made parallel in a pretty good way, okay? Because you can solve the pieces separately, and maybe you'll figure out a nice way to combine solutions or something like this. Okay? So when you try to come up with parallel algorithms, this is usually what you want to do. Okay, so you want to separate the problem into non-interacting pieces. Okay, and that's the goal of divide and conquer. Okay. And the second thing is, this almost by definition, you want an algorithm that's not too sequential. Okay, so but what do I mean by that, right? So let's look at the algorithms we've seen for flows, right? So hopefully all of you remember that we did flows. Okay, so what was the algorithm? Anybody remember? Sorry? Yeah, so it was called the Ford-Fulkerson, but how did it work?
You had to build this weird reverse graph, the residual graph.
Yeah, so essentially what we're doing is, you started off with some flow, okay, and then you build this weird residual graph, and then you try to find what was called an augmenting path in these graphs. Okay, but if you notice, it was a very sequential thing, right? So you find one flow, construct this residual graph for that flow, try to improve that flow a little bit, construct the residual for that new flow, try improving it, and so on. Okay? And the number of iterations of this operation was usually pretty large. Okay? And these are the kind of problems that are very, very hard to parallelize. Okay? So in fact, this is a big open problem. So if you have matchings, so this is like the Santa Claus problem we keep seeing. So if you have matchings in general graphs, trying to see if you can find parallel versions of this is one of the big open problems in computer science. Okay, so this is it's called POSNC. So it's not POSNP, but it's NC is a very different complexity class. But never mind that. Okay, so usually these kind of local search or improvement type algorithms are hard to parallelize. Okay. So that's something to keep in mind. Okay, so greedy algorithms, you can often do some tricks and make them parallel, even though usually you make decisions one by one. Okay, so you can often make a bunch of decisions at once, and if the overall thing works, it works even if you make a bunch of decisions at once. Okay, so that's so that's one of the things. But yeah, so this is one aspect of computation that we never spoke about in the class. Okay, so, but there is entire courses dedicated to this. So there's a parallel algorithms course here. I don't know how frequently it's taught, but it's taught at least once in 2 years. Okay, so if you guys are interested in parallelism, one interesting course to take. Okay. Alright, so the other thing we spoke a little bit about is optimization formulation, right? So, yeah, we spent a reasonable amount of time on this, and the point was you have some usually discrete problem, try to phrase it as some kind of an optimization, and now the optimization can't usually be solved efficiently, so you try to relax it to something that you can actually solve efficiently, and now you hope that this solution can be useful. Right, so that was the relax and round kind of paradigm. Okay, but in practice, optimization formulations are usually quite slow. Okay, so either you have to relax way too much to make it tractable in practice, or you may have to work with some reduced inputs. Okay, so where you sample or do something like this. Okay, so there's also this other slightly smarter way of sampling you could do called core sets. So, if any of you have taken data mining or plan to take data mining, you'll see a lot of this. Okay, so these are often ways to like reduce the data size to something that is manageable, and then you solve some, expensive optimization on this. Okay. So that's often the way it works. And we spoke a little bit about linear programs, but we didn't get to talk much about convex programs. So linear programming is one very specific kind of optimization. Right? So it turns out there's lots of other interesting things like eigenvalues. So this, some of you who are doing spectral clustering as your project are looking at it, and we, I guess, looked at it very briefly. Okay, and there's something called semi-definite programming. Okay, so this is something I wanted to do, but again we didn't have time. And yeah, so these are the kind of things you do in optimization. Okay, and there is this whole area which there's this whole very powerful notion called duality, where you have one convex program and the optimum value of that is related to the optimum of a different convex program. Okay, and it turns out these two problems are kind of well connected to one another. Okay, so we saw a very isolated example of this, where we saw that max flow equals the min cut. Okay, so this is one place where you might have seen this result as like an isolated cute fact, okay, which is true, but it's also part of this very general theme called duality. So we saw that the minimum cut in a graph is equal to the maximum, or rather if I fix some s and t, the minimum cut is equal to the maximum amount of flow that can be sent from S to T. So this is what we've seen. Okay. So yeah, so these all come under optimization, and very often you have some optimization problem. Maybe it's too hard to solve, but maybe the dual is easy to solve. Okay, so that's the reason it figures into this. Okay. So, but anyway, these are just things that if you're interested, you can go read up. Alright, so what are the morals, right? So what is something you should be, if you don't remember the details, these are the kind of things you should remember from the course. So one is, of course, thinking in a principled way, right? So you try to analyze when algorithms work and when they don't. Okay, so this is something you've hopefully learned from the course. So it's, and the other thing is, you've got to be able to figure out if a problem as phrased is too difficult. Okay, so this is why we had this, because as I was saying, how you phrase a problem often matters a lot, and this is an important question. And the other kind of a thing you've got to keep in mind is that sometimes you can come up with efficient algorithms all you want, but there's a limit to how much you can do this. So quite often you might have to see if sampling or estimation is useful. Okay? If your data is too big, you can't work with the whole thing no matter how clever you are. Okay, so that's reality you have to come to terms with. Okay, and so that's why some kind of estimation is often necessary. Okay, and we saw methods to see when a sample gives good information. Okay, so this is why we did all these concentration bounds and so on. So what we did are in very simple cases, but in some sense they give you a sense of how you think about these things. So more complicated versions are not that much more complicated if you are good with the basics. Okay, so that's why we did these basic concentration bounds. And this other takeaway from the course should be that in some sense when you think of a problem, don't just think combinatorial. Try to see if you can phrase it as an optimization. Try to see if you can do something more interesting. So that's, yeah. So often there's a tendency for students to just like jump in and try to think of the first heuristic they can apply, right? So sometimes it's just good to take a step back and try to see, what kind of algorithm should I try? Maybe can I phrase it as some optimization? Can I solve some smaller portion of the problem and then generalize, something like this. Okay, so these are kind of things you should take away from the course. And often, and of course the most important thing is this, so you need to be able to reason out, oh, so this algorithm is going to work for such and such reason, right? So that's something hopefully you've all gotten from the course. So I think that is it. So I wanted to, for the rest of the day, I just wanted to do a quick recap of things we have covered. Okay? So if you guys have already done this, so this is, in some sense, this is how you prepare for an exam, right? If you have an exam in a few days, then try to go over what all you've done. So I just tried doing something like that, like what we've covered and so on. Okay, so I wanted to do that. But any general thoughts on this? What I've been saying? Comments? Alright, so what have we done, right? So this is just a very quick overview. Okay, we started out looking at the basic paradigms, right? So in some sense we had like a few parts to the course. So we had like these essentials in some sense, and then we did essentials of graphs, because graphs are usually how we represent data. And we did a little bit about NP-completeness, and we had these other portions that I'll come to later. Okay, so let's look at these basic paradigms first, right? So we did a few things, and this was also a way of getting you guys to think more formally about problems, write proofs, and so on. Okay, and one of the first things we did was divide and conquer. So if you have a problem, how you break it up into pieces, solve the pieces, put them together, right? So we saw, like the only non-trivial example that we saw of this is this multiplication, where putting things together had to be done in a clever way. Okay, and then in the homeworks you guys figured out a much better way of doing it and so on. Okay. So this is, and usually if you have divide and conquer algorithms, you analyze them in an inductive way, right? You prove that by induction, the subproblem had to have been solved correctly, and then you only have to reason about this combination step. So that's how you analyze divide and conquer algorithms. And often the running times are very simple to reason about also. You just look at the algorithm and write down a recurrence. So this is how we did divide and conquer. And then we looked at dynamic programming. And the idea here was again, it was basically very similar to divide and conquer, but it's just that you had sub-problems that were appearing multiple times, and somehow the goal was to memorize the answers to these sub-problems. And the idea was to memorize the answers to these sub-problems. And often what we had to figure out is how you represent this sub-problem, right? Because naively there are just way too many sub-problems. Okay, so you've got to observe something structural about the problem and say that, okay, only sub-problems of this kind matter. Okay? And that's the whole game in dynamic programming, right? So trying to figure out what matters in a sub-instance. Okay? And now you have a succinct representation of your sub-instance, and then you have and then you just memorize answers to all those instances. So that's what we did in dynamic programming. And here the non-trivial example we saw was this traveling salesman problem. We came up with 2 to the n as opposed to n factorial time algorithm. Okay, so this is, yeah, so it's a battle between 2 giants, right? But it was, but one is much smaller than the other. Okay, so all right, so that's dynamic programming. Okay, and then we, of course, so greedy algorithms is something we touched upon, and here the idea is very simple. You just you want to build a solution, you build it step by step, you keep making the best choices. Okay, so this is generally the idea behind greedy algorithms, and the main step is that you never backtrack, right? So you always just build up your solution iteratively, and you keep making some hopefully good decisions at every point. You hope for the best at the very end. Yeah, and we said that usually greedy algorithms don't work. And very rare cases like spanning trees, where we could show that it actually works well. And even in those cases, the analysis are often pretty tricky. Okay, so you've got to say that, there exists some optimal solution where this choice is correct, and stuff like this. Okay, so this is how we had to argue about greedy algorithms. Okay. And so they're usually suboptimal. Locals are a little bit better, so it's kind of like greedy, but you don't build a solution. You start with some solution, which is feasible and everything. You try to improve it slightly. Okay, so you try to make some small moves, like swap edges or do something like this, so that you improve your solution. Okay. And the idea behind local search is that if your small moves are big moves, then you essentially cover the whole space, right? So then you find the optimal solution. But if you only look in, if you think of like all possible solutions in some geometric sense, you try to move to your neighbors until you hit some optimum, and then you stop there. Okay? Until you keep increasing your objective value, then you stop at that point. So that's the idea behind local search. And obviously, the bigger your neighborhood, the better your algorithm will be, and often there's this trade-off, right? So we saw it in the Santa Claus example, where we said that if I do only like 2 swaps, then we could show that the algorithm was about a factor half of the optimum. Okay, but if you did like more expensive swaps, like try every triple and try to see if you can do some better swapping, in your homework you saw that it actually does something like 2/3 the optimum. This kind of trade-off is normal, right? So it's like saying I have a solution, I look in a bigger neighborhood, then I'm kind of covering a wider set of possible solutions. Okay. So that's the idea in local search. So these are all very high-level descriptions. So these are like some of the basic paradigms, and there's other basic paradigm of randomization, which I'll come to later. But so these are like the essentials that you'll need even in the future. Okay. So, and then we started looking at basics of graphs. Okay. And here, so this is more of a recap. So most of you would have seen these in your undergrad as well. Okay, so like shortest paths, trying to find spanning trees and things like this. Yeah, but the interesting thing here which we saw was flows, and the reason we did this here is that it's an algorithm which is slightly different. It's better than local search in a way, in the sense that local search usually just tries to look for neighboring solutions. This one actually tries to augment solutions in a non-standard way. Okay. And this is what we called, so this was this residual graphs and augmenting paths that we just spoke about. And and it's a clever algorithm, and it's a clever way to correct mistakes that you make in a greedy algorithm. So this is pretty rare, and it's pretty rare. So it's one of the few cases where you can actually do this. Okay. And as I was saying, so we also saw this max flow min cut theorem, which kind of is a taste of this very general thing called duality. Okay, so max flow min-cut theorem. So it basically says that if I fix a source and a sink, maximum amount of flow I can send from a source to a sink is equal to the size of the smallest cut. So this is something you should know. All right, so that's that. And then we spoke a little bit about NP-completeness, and the guiding, motivating question here was, of course, this thing that are there problems that you don't expect to solve efficiently? And this was this, and of course by efficiently we mean polynomial in the input size. And for some problems this notion of input size was tricky. Right? So if you remember, we said that for factoring, for example, if I write a 100-digit number, the amount of space it takes for me to write down the number is only 100. Right? So, I mean, the number is huge. Okay, so that's what we mean when we say efficiently. And the general kind of intuition was that there are some problems, for example, this problem called satisfiability, where in some sense exhaustive search is the best you can do. We said that if you had a circuit with a bunch of inputs, x1, x2 up to xn, this is like a Boolean circuit, and so these variables are true or false, and all these gates are and or not gates. If you had a circuit like this, and if I ask you, do there exist inputs so that the final output is 1? So this was the satisfiability problem. And yeah, so as we discussed, we don't know of any better algorithm than this, than trying all possible inputs. Because this is a pretty complicated computation. So, I don't know how many of you have looked at this, but I posted this link to a very old paper of John Nash, not paper, like a letter that he had written to some army generals at some point. So you should take a look. So he discovered this notion of interactability long before computer scientists were thinking about it. So the announcements page, maybe discussion. Okay, and right, so this is the question, right? So the question is, you have this problem of figuring out if there exist inputs such that the output is 1. And now, so we don't know how to prove statements like this, and this is what is called the P versus NP problem, trying to prove that this problem does not have any polynomial time algorithm. Okay, and this is one of the biggest questions in computer science. We said that it has a lot of applications, for example, I mean in the sense that if this problem is hard, then you can do some kind of cryptography and things like that. Okay, so there's some good uses to problems being hard, right? So it's like saying deciphering something is hard. Okay. So I don't know if we spoke about it. Did we speak about it? Maybe not at length, but yeah. So okay. So cryptography often relies on certain computational problems being hard. Okay, so that's something you should know. And yeah, so as I was saying, we don't know how to prove that these problems are difficult, and that's the P versus NP question, but we believe that they are difficult. And in the absence of a proof, the best you can do is now reduce between problems, and this is what we saw. Okay, so what we said is that if you assume SAT is hard, that is, it does not have any polynomial time solutions, algorithms, then you can show that a whole bunch of other problems are difficult. Okay. So then a whole bunch of other problems are hard as well. Okay. This is the idea behind reductions. Okay, so you try to say that if I can solve this problem, I can solve SAT also. So you reduce from SAT to this problem. And yeah, of course, you've got to reduce in the right direction and so on. Okay, So building reductions is often an art. So, but we saw very simple examples. Alright. So any questions so far or any comments? Anything I've missed out by the way? Big things do you think? I mean, it's highly possible. I was just looking at my slides and making this, but yeah. Alright, so these are kind of what we did, very high level. Okay. And then we spent some bit of time about randomized algorithms. And in some sense, the high level aim in randomization is to take advantage of luck. Okay? Like, if I tell you that there's a whole bunch of good solutions, finding one is a matter of just randomly picking a solution. So that's kind of the overarching idea behind randomization. Right? So there are plenty of good solutions. Good solutions. You don't have to like really search for them. Then a random one would work well. So that's kind of the general theme here. And yeah, so we saw a bunch of examples of this. Like one was quicksort, and I guess the example we saw in detail was this question of selection. Right? So I give you an unsorted array. I ask you to find the kth smallest element. So earlier in the course we had seen an algorithm for this which runs in linear time. I mean, linear because you don't have to sort the thing. If you could sort it, then okay, you can just pick the kth smallest thing, right? But without sorting, how do you find the kth smallest element? Right, and this is something we saw. We said that if you do what is called as random pivot, where you pick an element at random in the array, and you divide this array into two pieces, then with good probability they'll be like roughly equal pieces. Okay, so you can do some kind of divide and conquer. Okay, and that was the idea. Okay, and again, what we relied upon is the fact that if I picked a random element with a pretty good probability, it's going to break this array into kind of balanced pieces. Okay. This goes back to what I was saying. Like there are plenty of good solutions. Random one would work pretty well. So this is something we did. And of course, when we talk about randomized solutions, there's always a probability of failure. Okay. So what you hope to prove is just that you hope to prove that your solution is correct with a good probability. Or you might want to prove that the expected running time is small. Okay. There could be algorithms where the running time could be very bad with some probability. You want to show that with high probability the running time is also slow, is also small. Okay, so that's what we wanted to show here. Okay, and of course we saw a whole bunch of results about how good are some estimates. Right? So if you randomly sample something and compute some quantity of interest, then is it going to give you a good estimate? Like one very simple example we saw was predicting election results. Right? So many of you seem to have had problems with that homework question, so you probably know that very well by now. Okay? That if you want to predict election results, then a small sample gives you a pretty good estimate if you had a good bias to start with and so on. Okay? So that's what we studied. We want to study here. Okay? So this general question of how good a small estimate is. Alright. And for this you needed a bunch of analysis tools. So we had all these tricks like linearity of expectation, concentration bounds and so on. Okay, so these are how you analyze, how you make formal statements of this kind. Okay, like the algorithm is going to be correct with high probability and so on. So alright, so this is just a very quick summary. And there's also some cases where we saw that randomness can have some unexpected power. Okay, so you saw some stuff in the homeworks. We also did a couple of examples in class. Okay, so we said that you have a whole bunch of numbers coming at you and you want to find out how many distinct numbers are there in this stream. Then we said that there's a very simple randomized algorithm that can actually do stuff. And okay, so this is not factoring. This is This would be nice, but just checking if a number is prime. Okay, so yeah, so this again is a problem for which there's a much simpler randomized algorithm than a deterministic one. Okay, so now people also know deterministic algorithms, but the randomized ones are very simple. So yeah, so randomness could have some unexpected power. In other cases where randomness is often used in practice is hashing. So you have a bunch of unsorted things, and so hashing, I think of it as some way of getting order in some unordered thing, right? So you have, let's say, huge sets of strings. You don't want to deal with these strings, you want to deal with some clean, ordered set of stuff. So you could hash them, and this often gives a good way of dealing with them. So it's, and in practice, hashing is very useful. Okay, and of course, randomness is often used for estimation. Like you have a lot of things, and you're too lazy to compute, or computation takes, I mean, yeah. So why do you want to compute when you can estimate, right? Very often, estimates are good enough. Sometimes estimates are probably even better than that. Okay, so yeah, so that's some, I mean, yeah, so that's kind of where randomness is very useful. All right, so that's all about randomness. Then we start looking at optimization, and here we had a very simple recipe for this, right? Which hopefully all of you have imbibed. It is, you're given some problem, and you've got to identify what are the right variables, what are the right constraints. I mean, usually a problem will have some constraints, and try to maximize or minimize some objective. Okay? So you've got to identify these aspects of the problem. Then writing down an optimization problem is often pretty straightforward. Okay? At least the first cut is very straightforward. Okay? But often the formulation you get will be hard to solve also. If your original problem was hard, this would also be difficult. So you've got to come up with solvable versions of this, and these are what we call relaxations. Okay, so the popular thing we saw are linear programming relaxations. Okay, so even if you're not submitting homework 6, I would encourage you to look at the problems. Okay, so just to get a sense of, you know, just to kind of learn more concretely about relaxation. Okay? Good question. Alright, so now once you relax this optimization problem, you could now come up with spurious solutions. Okay, so this was the big problem we saw, like for independent set, you have an extremely bad spurious solution in which all the variables were equal to half or something like this. Okay, so you could have spurious solutions, but they might still give you some information about the true optimum. Okay. And this is what we saw, this randomized rounding, these kind of rounding algorithms, where you came up with a solution that was not valid, but you used that solution to come up with something that was fairly good. Okay, so that was the idea behind rounding. And yeah, so if you saw, I don't know if it was last year's final or the practice final, maybe last year's final. So you can see some cases where, I mean, if your solution is, I mean, some cases a solution can be more useful than other cases. Okay? Like it's still a spurious solution, but it will give a much better approximation if it satisfies some conditions. And in practice, often that's the kind of thing that works. Okay, so in practice, especially for problems like scheduling and so on, people observe that if you just write some linear program relaxation, it actually finds the exact right solution, okay, except for some few variables that are confusing. Okay, so in practice, this is more useful than you would think. Yeah, so that's the other thing that I wanted to state. Okay, so this is what we had done. Right, in the last couple of weeks we did a bit more additional topics. So these are not things that I'll probably test you on. These are not things I will test you on. But things like online algorithms, where somehow the goal was you wanted to make decisions but with limited information, right? Like you don't know future events. Like we saw this example of caching, right? So you get page requests. You know only the requests you've seen so far. You don't know what is going to come in the future. But you've got to make decisions about which pages to evict. And you could make bad decisions, and then you would incur a lot of loss. But the hope is that you would still be able to compete with the optimum in hindsight. And this is what we call the competitive ratio. We said that you can often have a pretty non-trivial competitive ratio for problems. Okay, so even though you have no idea about what's going to come next, you will still not make too many more mistakes than the optimum thing in hindsight. Okay, so it's a very surprising fact. And again, it's not very surprising in hindsight, but it turns out randomness helps a lot here. Okay, so I didn't spend any time on this, but very often, so if you make decisions using some kind of a random strategy, then it's even though you don't know the future, you're kind of insured against a whole bunch of possible things. Okay, so unless you're very, very unlucky, you will be doing somewhat okay. Okay, so that's why very intuitively randomness helps. Okay, like if you have a deterministic strategy, you can imagine an adversary constructing an example that's going to make you do badly at every time step. Okay, but if you had a random strategy, then the adversary doesn't know what coins you're tossing. Okay, so in some sense, the adversary does not. Yes. So you won't be able to do. You won't be doing that bad. Okay, so this we didn't touch on this, but randomness helps a lot when you're making decision making with limited information. Okay, so that's just something to keep in mind. Then we saw this robust computation that I spoke about earlier. Okay. So it's how you do reliable component with faulty reliable computation with faulty components. And this is where things like error correcting codes show up. Okay, so this, as I said, as I promised, it's the course in 30 minutes. Okay, so we've, so this is just a rough outline of stuff we have done. And so that's it. And if you have specific questions about the homeworks or something like this, I can cover them in next class. Okay, and so if you have general feedback on the content of the course, like like some parts of it were way too advanced or something like that, just send me email or just discuss with your friends and send me email or something like that. So that's so this course has been evolving in the sense that we've tried like multiple options, and this seems to be the one that has a mix of classic stuff and some new stuff. Okay, so so there were earlier versions of this course where it was mostly these early topics, and then those would be more like an undergrad course, and it's not really a grad level course. But there was Suresh did a version where he started off with randomness, and then apparently nobody got anything much out of it. So it was so this we thought is a compromise. So if you have comments on the content or relative proportions of how well we did, then just let me know. Happy to incorporate them. Okay, so assuming they're reasonable. You can't say this is nonsense. Okay, all right. So that's it. And next class, you're free to, by default. Do you guys want me to just go over the practice final and last year's final or something like this? So that will be the default plan. And if you have homework questions that you wanted to talk about, I can do that also. Okay, so just write to me before. All right. So, see you.